Welcome to the 11th lecture on the category of vector spaces, titled Dimension of Spaces of Linear Functions. In this lecture, all vector spaces are over a fixed field K. Let's review from the previous lectures the tools we will need today. If V and W are vector spaces, the set of all linear functions from V to W is itself a vector space. A vector space is finite dimensional when it has a finite spanning subset. A finite dimensional vector space has at least one basis, and all bases of that space have the same cardinality, which is finite and called the dimension of the space. The dimension is a complete invariant of finite dimensional vector spaces up to linear isomorphism. If V and W are finite dimensional, a very natural question is what can be said about the dimension of the space of linear functions from V to W. This will be the topic of this very important lecture, where we introduce the notion of matrices. Let's begin with answering the question in a very important special case, namely the case of the dual of a vector space. So the algebraic dual, E star, of a vector space E is a set of all the linear functions from E to the scalar field. I will refer to this object just as a dual, and I will note that the elements of the dual are called linear functionals. The main theorem about duals in this lecture is the following. If E is a finite dimensional vector space, and if V1 etc. Vn is a basis of E, we can define a linear functional V star j on E for every j between 1 and n as follows. V star j is a unique linear function from E to the scalar field, such that for any k between 1 and n, V star j at Vk is 1 if j equals k, and 0 otherwise. Since V1 etc. to Vn is a basis, these relations are indeed sufficient to define a unique linear function on E valued in the scalar field. And the conclusion of the theorem is that V star 1 etc. V star n is actually a basis for the dual. In particular, we see that the dimension of the dual equals to the dimension of the space. To prove this result, I want to show that the set V star 1 etc. V star n is a basis, so I first prove that it is linearly independent. Let T1 etc. Tn be scalars, such that T1 V star 1 plus etc. plus Tn V star n equals to 0. Let k now be an arbitrary integer between 1 and n. I'm going to apply these 0 linear combinations here to the vector v sub k. So I get 0 equals the sum from j equals 1 to n of t sub j, v star j applied to v sub k. But now know that v star j applied to v sub k is 0 all the time except when j equals k, where it is 1. And so what we are left with in this sum is simply the coefficient t sub k. So we have shown that for any k between 1 and n, t sub k is 0, which means that v star 1 etc. v star n is a linearly independent subset of this dual E star of E. Let's now prove that this set is also spanning. So let phi be an arbitrary linear functional over our vector space. Write psi as the sum from j equals 1 to n of phi of v sub j times v star of j. So psi, by construction, is a linear combination of the vectors v star 1 etc. v star n in the dual. So in particular, know that psi is a linear functional itself. Now I'm going to prove that phi and psi agree on the basis v1 to vn. So again, let k between 1 and n. Let's calculate psi at vk. Well, it is the sum from j equals 1 to n of phi of v sub j times v star j at v sub k. And again, v star j at v sub k is 1 only when j equals k and 0 otherwise, so just as before, all what is left of this sum is the value phi at v sub k. So you see that psi at v sub k equals a phi at v sub k for every k between 1 and n. So psi and phi agree on a basis of E, and therefore as linear functions that agree on a basis, they must agree on the entire space, and so psi equals phi. which means that phi is in the linear span of the set v star 1 to v star n. Since we also know that v star 1 to v star n is linearly independent, it is a basis for the dual space, and by counting how many elements it has, we can conclude the dimension of the dual space equals the dimension of the original space. The basis v star 1 to v star n is called the dual basis of the basis v1 to vn. It enjoys a very nice property. So again, with the same notation, v1 to vn is a basis of a vector space E. Then if you pick x, an element of E, x is of course a linear combination of the vectors v1 to vn, and the coefficients are actually unique. It turns out that we can use the dual basis to calculate those coefficients. Because if you apply for some k between 1 and n, the linear functional v star k at x, then you see that by linearity this equals to the sum from j equals 1 to n of the coefficient t sub j times v star k at v sub j. And again, v star k at v sub j is 1 only when j equals k and 0 otherwise. So again, we recover the coefficient t sub k. We've seen that in the proof of our main theorem. But that means simply by substituting t sub k by v star k at x that we get this very nice expression for the vector x. It can be written simply as the sum over j from 1 to n of v star j at x times v sub j. So the dual basis essentially reads the coordinates of a vector in the original basis. We also know that if E is finite dimensional, then our result here proves that the space E and its dual are linearly isomorphic, since they have the same dimension. However, the isomorphism depends on the choice of a basis. Indeed, if you give me a basis of E, I can make a dual basis, and then I can make a linear isomorphism which maps the original basis to its dual basis in an obvious fashion. But if you change the original basis, then you change the linear isomorphism and the dual basis. It is of course something to be expected in general. If you have two finite dimensional vector spaces with the same dimension, then they are linearly isomorphic. But to get an explicit linear isomorphism, you need to exhibit a basis of both of those vector space and map one to the other. Now, of course, the dual of a vector space is itself a vector space, and so we can take its dual. So let E be a vector space. The bidual of E is the dual of E. And if E is finite dimensional, then with the work we have just seen, we can conclude the dimension of the bidual equals to the dimension of the original space. So again, the space and its bidual are linearly isomorphic when the space is finite dimensional. However, in this case, there is a natural isomorphism between the space and its bidual, that is, an isomorphism that does not require the choice of a particular basis. So let's construct this isomorphism. If E is a finite dimensional vector space, and if X is a vector in E, we define an element of the bidual of E as follows. The map J of X associates to any phi in the dual of E the value phi of X. So we see immediately that J of X certainly is a function from the dual to the scalars, and it's very, very easy to check that it is indeed linear. So J of X is an element of the bidual of E. And thus we have actually defined a map J, which goes from the vector space E to the bidual of E. And the claim of this theorem is that this map is actually a linear isomorphism. It is obvious that for a fixed x in the vector space E, J of X is linear. Then we note that J itself is a linear function. So we take two vectors x and y in E and a scalar lambda. And we calculate J applied to lambda x plus y. Remember, J applied to lambda x plus y is an element of the bidual of E. So it's a function with input being a linear functional over E. Let's call it phi. And what does it do to phi? It maps it to phi of lambda x plus y by definition. But since phi is linear, phi of lambda x plus y equals to lambda phi of x plus phi of y. And then phi of x, if you look, is by definition J of x applied to phi, whereas phi of y is by definition J of y applied to phi. So we can factor and we get that the expression j at lambda x plus y equal to the function lambda j of x plus j of y. So j is linear as well. Now I'm going to prove that j is an isomorphism, and since I know already that the dimension of E and the dimension of the bidual of E are equal, I can conclude that j is a linear isomorphism as soon as I have shown that j is injective. So if x is in the kernel of j, that is j of x is 0, then by definition it means that if you take any element phi in the dual of E, any linear functional of E, and you apply it to x, you get 0. Well, what we're going to do is we're going to pick a basis of our vector space E, which is assumed to be finite dimensional. Let's call this basis V1 to Vn. And let's consider its dual basis with the same notation as before, V star 1 to V star n. Now, V star 1, V star 2, etc. are all elements of the dual. And so when you apply them to x, we get 0. Therefore, using the observation we made on the previous slide, since x equal to the sum from j equals 1 to n of v star j at x multiplied by v sub j, and this is a linear combination whose coefficients are all 0, we get that x equals 0. So we've seen that the kernel of j is indeed the singleton 0, and thus j is injective. And thus, by the rank theorem, we can conclude, since the dimension of the domain and the dimension of the codomain here are equal, that j is in fact an isomorphism. We make the first remark that really is behind the introduction of this map j here, is that j is canonical. There is no need to choose a basis of E or a basis of the bidual to construct j. I used the basis, of course, in the proof of isomorphism, and that's important actually, but I did not need a basis to define j, so it exists sort of intrinsically. And in fact, if you look at this definition, it makes sense even if E is not finite dimensional, though it is much less clear if the resulting map j is injective or surjective. In fact, if you accept the axiom of choice, it is always injective, but it is usually not surjective. And if you don't accept the axiom of choice, it's not even clear if this map is injective in general. So now I'm going to use this result to show that if E is a finite dimensional vector space, then all the bases of its dual are in fact dual bases. So let V1 to Vn be a basis of the dual of E. Then this basis has a dual basis in the dual of the dual of E, which is the bidual of E. And let's denote that dual basis by V star 1 to V star n. Now, J, as constructed in the theorem, is a linear isomorphism from E onto the bidual of E. So what I can do is for any k between 1 and n, I can define E sub k as the image by the inverse of J of V star k. Since the inverse of J is a linear isomorphism, it maps basis to basis, and therefore E1 to En is a basis for E. I'm going to show that V1 to Vn is the dual basis for E1 to En. So let L and K be two indices between 1 and n. Let's calculate V sub L applied to E sub k. Well, by definition of J, this equals to J of E sub k applied to V sub L. But now G of E sub k by construction is V star k. So VL applied to E sub k is V star k applied to V sub L, which is 1 if L equals k and 0 otherwise. So V1 to Vn is indeed the dual basis of E1 to En. Now, inside of this construction, you might start wondering, if E is some vector space which I do not know is finite dimensional, but if its dual is finite dimensional, then can I conclude that E was in fact finite dimensional? And this construction here looks promising, except that at some point in it I use the fact that J is a linear isomorphism, and that in turn is a consequence of the fact E is finite dimensional in the proof of our theorem. So in order to get the desired property, either I would have to assume that J is a linear isomorphism, or I will need to have some additional assumption, and that's what we're going to see in the next theorem. So I'm going to prove the following result. If E is a vector space with a basis, and if its dual is finite dimensional, then E is finite dimensional. And of course, then the dimension of E is equal to the dimension of the dual of E. It's very important here that I assume the existence of a basis of my vector space E. Otherwise, I can't be even sure that the dual of E is not reduced to the singleton zero. So let's prove this result. First, observe that the bidual of E is also finite dimensional since it is a dual of the dual of E, and the dual of E is assumed to be finite dimensional. Also note that the map J we saw on the previous slide still makes sense. It is still a map from E to its bidual, though now I do not know a priori that this is injective or surjective. Then, by assumption, there is a basis for E. Let's give it the name V sub j for j ranging over a set K of indices, and note that this could be an infinite basis. Nonetheless, I'm going to introduce dual elements to this basis as follows. For each j in my index set K, I define V star j as a unique linear functional of E, such that V star j evaluated at Vk is 1 if j equals k, and 0 otherwise. Now, this is exactly what we've seen when we were working with dual bases, and in fact I could apply the proof of linear independence of dual bases exactly unchanged here to conclude that indeed V star j for j ranging over k is a linearly independent subset of the dual space of E. However, I cannot conclude that it is in general spanning. The reason is that you can certainly have an element of the dual of E which assign non-zero values to every single vectors V sub j. And so if the set K is infinite, then it would not be possible to write such a linear functional as a linear combinations of the vectors V star j. Nonetheless, if X is in the kernel of this map J, then again you can still conclude that V star j of X is 0 for all j in K, just as before. And again, using the fact that this vectors V sub j for j ranging over K form a basis for E, you can write X as the sum from K equals 1 to n of some T sub K, V sub j sub K, where the T sub K's are scalars and J1 to Jk's are some indices. Then by applying V star sub j sub K to X for K ranging from 1 to n, you get that the coefficient T1 to Tn are 0, just like before. So we can again conclude that X equals 0. But then that means that J is injective. Now, again, we still don't know that E is finite dimensional, so I cannot conclude that J is bijective right now. But what I can observe is that it tells me that E is isomorphic to the range of J, since J is injective. And the range of J is, of course, a subspace in the bidual of E. But every subspace of the bidual of E must be finite dimensional, since the bidual of E is itself finite dimensional. And since E is isomorphic to a finite dimensional subspace, it is itself finite dimensional. And then we're back to the situation where E is finite dimensional, so the conclusion about the dimensions follows from the work we have done so far. Now, we are ready to prove the main theorem for this lecture, which is the dimension of the space of all linear maps between two finite dimensional vector spaces. So if E and F are finite dimensional vector spaces, then the space of all linear maps from E to F is finite dimensional, and its dimension is a product of the dimension of E by the dimension of F. Let's prove this result. So, to simplify notations a little bit, as we are going to have a lot of notations here, let n be the dimension of E and m be the dimension of F. And we are, of course, going to extract a basis for E and a basis for F. So let's write V1 to Vn a basis for E and W1 to Wm a basis for F. Again, to keep things a little simpler, let I be the subset of the natural numbers between 1 and n, and j be the subset of the natural numbers between 1 and m. Now let's pick j between 1 and n and k between 1 and m. I'm going to define a linear map from E to F called psi superscript k subscript j as a unique linear map from E to F such that for any L between 1 and n, if you apply this linear map psi kj to the basis vector VL, you get WK if L equals J and 0 in all other cases. So basically, this is a map that takes the vector V sub J and maps it to the vector W sub K and map every other vector in the basis of E I have chosen here to 0. And let's write psi for the collection of all of those linear maps psi kj, where j ranges from 1 to n and k ranges from 1 to m. I wish to prove that this chi is a basis for my space of linear maps from E to F. So first I'm going to prove that the family psi is linearly independent. And to that end, as you recall, I will take a linear combination of all of its elements equal to 0 and prove all the coefficients of that linear combination must be 0. So let's call the coefficients t sub j superscript k for, again, j ranging from 1 to n, k ranging from 1 to m. And we thus form a combination which looks like this: sum for j equals 1 to n, sum for k equals 1 to m of t sub j superscript k, psi sub j superscript k equals 0. So what do I know about this? Well, I know I can apply this 0 combination. Remember, the 0 here is 0 as a linear function from E to F. I can apply this function to any vectors in E, and I will get 0. So in particular, I can apply it to a vector of the basis that I chose for E, that is V1 to Vn. So let's pick V sub L be an arbitrary element of that basis, and let's apply this function, which is 0, to VL. So we get 0 equals the sum for j equals 1 to n, sum for k equals 1 to m of t sub j superscript k, psi sub j superscript k of VL. But we can calculate, of course, these psi's applied to the VL vector, because most of them are 0 unless j equals L. That's by construction. And when j equals L, psi subscript L superscript k of VL is WK. That's what the superscript and the subscript are for. So 0 is indeed equal to the sum for j equals 1 to m of t superscript k subscript L of WK. All right, what matters here is that we found a linear combination of the basis vector WKs, which is equal to 0, and therefore all the coefficients of this linear combination must be 0. So we got that t sub L superscript k is 0 for all k and j. Since L was arbitrary between 1 and n, I can conclude that for all j between 1 and n and all k between 1 and m, the coefficient t superscript k subscript j is 0. Therefore, I have proven that psi is linearly independent. I want to prove that psi is also spanning. I'm going to use the same strategy as when I worked with dual basis, except that the notations will be more involved. In particular, I'm going to use the dual basis of W1 to Wm. Let phi be a linear map from E to F. Let's define this new linear map from E to F called psi, which is the sum for k equals 1 to m, sum for j equals 1 to n, of w star k applied at phi applied at v sub j times psi superscript k subscript j. Now this is a complicated expression, but we can at least check that it makes sense. For each j, you calculate phi at v sub j, and then you write phi at v sub j as a linear combinations of the vectors w1 to wm, since they form a basis for f, and the coefficient corresponding to wk in this linear combination, which is uniquely determined since, again, w1 to wm is a basis, is a value that w star k will take at phi of v sub j. That's a scalar that we then use to multiply this linear function from E to F called psi superscript k subscript j. And then we sum all of that. What's interesting here is to note what happens if you calculate psi at v sub j. for j between 1 and n. Now remember that the linear function xi superscript k subscript j by definition is 0 when evaluated at v sub l for l not equals to j, but it is actually equal to wk when l equals j. Therefore, if I plug v sub j in this expression, what I'm left with is a sum for k equals 1 to m of w star k applied at phi evaluated at v sub j times the vector w sub k. And if recall one of the main property of dual basis, this sum here, this linear combination of the vector w sub k, actually equal to phi of v sub j. So, psi and phi agree on the basis v1 etc. to vn. And therefore, since they both are linear, they must be equal on the entire space. So this shows that phi is a linear combination of the vectors in xi. So xi, which we know is linearly independent, also spans the entire space of linear functions from E to F, and therefore it is a basis for this space. So to conclude my theorem, it is sufficient for me to look at the cardinality of xi. But by construction, the cardinality of xi is simply the cardinality of the Cartesian product of the set 1 to n and the set 1 to m. In other words, it is the product of n by m, that is the product of the dimension of E by the dimension of F. And my result is proven. Now, actually, this is a very, very important construction. For the first time you see it, it may be a little bit complicated. Now, actually, the construction of the basis in this theorem is extremely important because it is what gives rise to the notion of metrics. Now, I'm going to make two simple observations about this theorem. First, note that we recover the result that the dimension of the dual of E is equal to the dimension of E for E of finite dimensional vector space by applying this formula to the special case where F is a scalar field, and thus the dimension of F is 1. Second of all, note that the dimension of the dual of a finite dimensional vector space equal to the dimension of that space. So this formula tells me that the dimension of the space of linear functions from the dual of F to the dual of E is the same as the dimension for the space of linear maps from E to F as long as E and F are finite dimensionals. So those two spaces of linear functions should be isomorphic, but the question is there a natural isomorphism between those two spaces of linear functions? The answer is positive and given by an important isomorphism called the transposition. So let's fix E and F to finite dimensional vector spaces, and let's pick phi a linear map from E to F. The transpose of phi is a map which to an element xi of the dual of F maps the element xi composed with phi, which is indeed an element of the dual of E. Indeed, the domain of xi composed with phi is the domain of phi, which is E. The codomain of xi composed with phi is the codomain of xi, which is a scalar field. And as a composition of two linear maps, xi composed with phi is linear. Now, it's easy to check that actually this transpose of phi is itself a linear map, which goes from the dual of F to the dual of E. And even better, the map that to a linear function phi from E to F associates its transpose from the dual of F to the dual of E is itself a linear isomorphism, which is called the transposition. So let's prove this interesting result. Again, linearity of the transpose of phi for phi a linear map from E to F and linearity of the transpositions are easy to check and in fact follow a pattern similar to what we did for the map J between a space and its bidual. But on the other hand, I want to prove that the transposition is not just linear but also an isomorphism. So let's first prove that it is injective. So let phi be a linear map from E to F, and suppose that phi of x is not 0 for some x in E. In other words, suppose that the linear map phi I chose is not a 0 map, so it's not 0 somewhere. Then there exists an element of the dual of F called xi such that psi applied phi of x must be 1. Now, why does that exist? Well, here we work in finite dimensions, so we have a lot of tools. So here's an idea. Phi of x is a non-zero vector of f. Therefore, the singleton phi of x is linearly independent. And therefore, I know I can form a basis which contains the vector phi of x. But then, I can take the dual basis for the basis I just made, and that dual basis, which lives in the dual of f, will have the property that in particular, it has one element which is 1 at phi of x. That's one example on how I prove the existence of this psi. But now if you calculate psi composed with phi and you apply that to x, you get 1, of course, by construction. And, well, 1 is not 0. So we see that if we have a linear function phi from e to f that is not 0, then its transpose is not 0 either. So that means that when the transpose of a linear function from e to f is 0, we must have that we started from a linear function that was 0 itself. That means transposition is injective. The kernel of the transposition is reduced to a singleton 0. But then, as I discussed, the dimension of the space of linear functions from the dual of f to the dual of e is, by the theorem we just shown before, the product of the dimension of the dual of e by the dimension of the dual of f. But that's the same thing as the product of the dimension of e by the dimension of f. And that, in turn, again by the result we have seen, is a dimension of the set of linear functions from e to f. So the transposition is a linear injection between two finite dimensional vector spaces with the same dimension, and therefore the transposition is actually linear isomorphism. This concludes our presentation of the computation of the dimension of the space of linear functions between two finite dimensional vector spaces. We now can progress in two different directions. Next, on the category of vector spaces, we will discuss the space of multilinear maps and an associated construction, the tensor products of two vector spaces. Since we also introduced a basis for the space of linear functions between two finite dimensional vector spaces, we are now ready to study the algebra of matrices, beginning with our first lecture called Matrices.